Chapter 5, Cluster 2, we're ready to look at radical functions. So radical functions are going to be those functions that have square roots or cube roots or something in them. We're going to start with some square root functions. So going to be defined by the square root of g of x, where g of x is a polynomial. And we're going to look at the graphs and the domains of those functions. We're also going to look at the positive versus negative square root functions, and then properties of those graphs. Okay, so let's check out our context here. We have people jumping out of hot air balloons. Okay, typically you're jumping out of an aircraft approximately 14,000 feet in the air and you're free falling before you activate your parachute. And then we can define the time in free fall, or the distance in free fall in terms of time. The distance in free fall, s equals t squared, 16t squared. So let's take a look at how far you would free fall if you were falling for 0 through 25 seconds here. All right. Okay, so I'll just put this up here. Here we go. We're going to start with our s of t function equals 16t squared. Make ourselves a table for s of x1. And we want to see 0, 5, 10, 15, 20, 25. Handy. Right. So if you have fallen for 0 seconds, you have fallen 0 feet. That one makes sense. If you've fallen for 5 seconds, you fell 400 feet. Whew. 10 seconds, 1,600 feet. 15 seconds, 3,600 feet. 20 seconds, 6,400 feet. 25 seconds, 10,000 feet. You're only 14,000 feet above the ground, so quick pull your parachute because you're only 4,000 feet up left. Okay, so this is our function, and if I look at my equation, I should recognize it. Let me zoom out as a parabola, and we might be wondering what this currently has to do with the square root function, so we're getting there. So currently, I have this parabola where, yes, it has both sides, but only one side makes sense in terms of the context right here because you can't fall before you started falling. Okay, so with the 16t squared, we recognize quadratic, so we think parabolic shape. The skydiver, though, needs to know how much time she has left in free fall before having to activate her parachute, and the time in free fall will depend on the distance in free fall. So suppose she jumps from the plane at 12,000 feet and must activate the parachute at 3,000 feet to determine the free fall distance. Okay, so she's going to be falling for everything except the 3,000 when she needs to pull the parachute. So she's going to be falling for 9,000 feet. And I want to know how long it's going to take because I can't measure the distance 9,000 feet. Like, you can't measure that and be like, oh, time to pull it. But instead, if we can plug the 9,000 into the formula, we'll be able to figure out what the time is, and she can set a stopwatch to figure out how long she's able to fall. Okay, so if I'm going to solve this by hand, I'm going to divide that 16 off of both sides. These ones on the bottom of the page are hard to show. My book just doesn't like to move up that far. Okay, so let's do our division here of 9,000 divided by 16. That's 562.5 equals t squared. And then the opposite of a square is a square root. So we're going to square root both sides. So that sounds good. That 23.7 is the amount of seconds that she's able to fall. Okay. Then she better pull her parachute so she doesn't splat. Now, technically, there are two answers to this. If I were to graph y equals 9,000 on this grid, I would of course see two answers to the quadratic, but we're ignoring this one over here because the negative time we know doesn't make sense. But I'm going to make a note of it real quick. When you take the square root of both sides, you should insert a plus and minus symbol in here because there are two solutions, but we are selecting the positive solution because we already established that the negative input values don't make sense. So there are two solutions to the equation, one solution in context. Okay, decimals out of my way, and over to our next page. Okay, the process of determining free fall would be simplified if my formula expressed t as a function of the distance s. So we're going to solve this equation without putting the 9,000 in for s. We're going to solve it for t. Okay, so same process. S equals 16 over 16 t squared. And we need to divide the 16 from both sides, just like we did before. And that'll cross off our 16, and we'll have s divided by 16 equals t squared. And then, same as before, I can take the square root of both sides. And that's going to give me t since the square and the square root are inverses. Now, in the square root of s over 16, I can simplify a little bit because I already know the square root of 16 is 4. So I can write this as the square root of s over 4 equals t. So that's going to be our simplified version of this equation. All right, so let's take this equation. And when I write it over here, I'm going to use it as in function notation. So instead of t, I'm going to do t of s equals the square root of s over 4. And then I can get my table going, and I can do t of x1 and plug in the values of 0, 400, and so on. Okay, so it's going to take, if you fall for 0 seconds, or sorry, if you fall for 0 feet, it's going to take you 0 seconds. If you fall for 400 feet, that'll take you 5 seconds, 10 seconds, 15 seconds, 20 seconds, and 25 seconds. And then we'll sketch this graph. All right. Okay, so this is the graph modeled by this function. Note these two functions are the same. It's just that they have written it in decimal form. Instead of 1/4 square root of s, 1/4 is a decimal 0.25. So I think that more naturally it came out this way, but if you prefer to write it into the decimal form, that's okay. 1/4 square root of s or 0.25 times the square root of s. And either way, that's what your function should look like. How are the ordered pairs in this table related to the ordered pairs in this table? They are flip-flopped. They are reversed. The x became the y and vice versa. And that's because these functions that have those reversed input and output values, they are inverses. We talked about inverses in chapter 2 and a little bit more in chapter 3. So those are inverse functions of each other. All right. So considering the general function, not in terms of skydivers anymore, but just the general function, what is its domain? All right. So when you saw this graph on decimals, did you notice that it does not go past 0? It's like a hard stop there. It does not have an asymptote like our logarithmic graphs had done so. It does not go into the negatives. 0 is the first value you can plug into it. Because I am not able to put a negative inside the radical. Well, I could, but it would give me an imaginary number, and it's not going to show up on a graph. So the imaginary numbers are not going to be real inputs. So the domain is a set of real numbers in which I can evaluate. So 0 is the first one. 0 itself is okay. So again, unlike our logarithms where 0 is not okay, it parenthesizes 0, I can plug 0 in. If I fell for 0 feet, I fell for 0 seconds. There's a meaning at 0, and there is an accepted value at 0. And then this graph's going to go on forever. So we're going to go up to infinity. If we have lost sense of context, just looking at the function itself, it's going to be hard bracket 0 up through infinity. Sketch a graph. Well, the graph is not going to look too much different if I'm looking at it on the general domain versus on the practical domain. So I'm just going to draw it again. That's what it looks like. All right. And what is its range? Okay, so the range is the outputs. So the first input, x value available, was an input of 0, and then we went all the way to the right, inputs all the way to infinity. The range, the first output, is also 0, and I do achieve an output of 0. And then up, I'm going all the way up to infinity. I don't go into the negatives, but I do get 0, and I do achieve 0, so hard bracket 0 up through infinity. So the domain and range of these two are the same. With modifications, it might change, but for right now, they are both from 0 to infinity. All right, now this could also be written in inequality notation if you prefer. So you could have written y is greater or equal to 0 if you prefer inequality notation. Same thing over here. We could have written or x is greater or equal to 0 if you prefer inequality notation instead of interval notation. You can do that. Okay, so recall that the square root of a negative number is not real, therefore the domain is defined by the set of all numbers for x such that g of x, the inside of the function, is equal to 0. So the inside of our function was just x, or s, or whatever you want to call it. If we generalize this, whatever is inside the function has to be greater or equal to 0 in order for this function to have a real valued output. Okay, so we're going to look at the domain for more general functions. So first of all, for our f of x function, we're going to talk about our function and its domain. So I'm not going to write the word domain, I'm just going to put the domain over here. For f of x, its domain, since it's the square root of x, we need x to be greater or equal to 0. All right, so for g of x, inside the square root is x plus 2, so we need x plus 2 to be greater or equal to 0. So if I solve that and subtract 2 from both sides, what this means is that x needs to be greater or equal to negative 2. So the domain for f of x is x greater or equal to 0. The domain for g of x is x greater or equal to negative 2. And then for h of x, what's inside the square root, that's x minus 3. X minus 3 needs to be greater or equal to 0. So if I add 3 to both sides, that means that x needs to be greater or equal to 3. So the domain for h of x is x is greater or equal to 3. And again, each of those could be expressed in interval notation if you choose, instead of inequality notation. So write the interval notations for those on the side. Sketch 3 graphs. Okay. All right, so the first one was just the square root of x. The second one was the square root of x plus, the square root of x plus 2. And the third one was the square root of x minus 3. Okay, so as we can see from these three pictures, f of x, 0 is the lowest input allowed. G of x, negative 2 is the lowest input accepted. And h of x, 3 is the lowest acceptable input. So I could draw myself a graph of f of x, g of x, and h of x like this. Are the functions increasing or decreasing? They're all increasing. Every one of them is heading up and over as they move from left to right. Their y values are increasing. All right, so moving on, we're going to look at f of x equals the square root of x versus g of x equals negative the square root of x. Determine the domain and range for each of these. Okay, so we'll do a little table here for domain and range. And f of x equals the square root of x compared to g of x equals negative the square root of x. Okay, so the domain for f of x, we already know this one. It's that the inside x has to be greater or equal to 0. For g of x, the inside of the square root, which is x, has to be greater than or equal to 0. So their domains are the same. The range for the square root of x, we saw this one before. It's also y, this time, has to be greater or equal to 0. But if I have a negative the square root of x, What is that going to do to the graph? Let's take a look at it first. If I have a negative square root of x, flips my graph over. I'm going to shrink this down a little bit. And I can see that instead of having positive outputs, I have all the negative outputs. So instead of going y greater or equal to 0, we're going to say that our range is y is less than or equal to 0. And again, I'm going to write those two in interval notation just to compare. This would be 0 to infinity. This would be negative infinity up to 0, because it's always in order, and so 0 is the largest value this time, so it's going to come second. I just wrote the ranges. Both of these domains would be 0 to infinity if you were to write them in interval notation. So one of these functions is like that, and the other function looks like that. Same thing, they should be symmetric, just one points towards up, one points towards down. How would you obtain the graph of g from the graph of f? Reflect it over the x-axis. Okay, so determine the domains of these two functions. Okay, so for the first one, we need x minus 3 greater or equal to 0. So if I add 3 to both sides, I want x greater or equal to 3. Okay, so the domain for h of x is greater or equal to 3. And for capital F of x, I want 3 minus x is greater or equal to 0. So if I subtract 3 from both sides, that's negative x is greater or equal to negative 3. And I'm going to divide both sides by negative 1. When I divide by a negative, I flip the inequality sign, as we studied in chapter 1. So I flip the inequality sign because I just divided by a negative. So this is going to be x is less than 3. That's going to be our domain for f of x. Okay, tables and graphs. So one of these we want to be x minus 3, and the other one we want to be 3 minus x. All right, so like we said, the domain for one of them is 3 and higher. That's this one. And the domain for the other is 3 and lower, x less than 3, and that's this one. All right, so in a table, sorry, my book is in the way, I have to move it a little bit. And in our table, we want inputs of, different inputs, darn it. All right, so we'll just do the inputs for one and then the other. 3 is going to be the same. So the input 3 for f, which is the top function, is 0 and 0. And then we'll do 4. I want 1 here. I'm going to do the top function first. 7, that's 2. Maybe I could just do them all. Nah. 12, this one's 3. 19, this one's 4. There's just too many values to do all of them. And then 28, this one's 5. Okay, now these are all undefined for this because I can't plug in numbers bigger than 3 into this function. It can only accept numbers less than or equal to 3. So 3 is the only overlapping value. So for the next function, I can plug in 2, and I get 1 as the output. I can plug in negative 1. Goodness, too many backspaces. I can plug in negative 1, and I get 2. I can plug in negative 6, and I'll get 3. Negative 13, and I'll get 4. And negative 22, and I'll get 5. Okay. And then sketch the graph. Okay, so x equals 3 is where they met up. And that's how they look. One was heading to the right from x equals 3. The other one was heading to the left from x equals 3. So are they increasing or decreasing? So h of x, which is the first function over here, this was h of x, is increasing. And this is our function f of x. Functions have to be read left to right. So if you're going in this direction, left to right, it's decreasing. So f of x is decreasing. You can't think about these as coming from 3. They both come from negative infinity. This one decreases until it gets to 3. Then at 3, this one starts and it increases. So you're not looking at them outward, looking left to right, decreasing and increasing. All right, another function to look at here. First of all, it's domain. And so we're going to do the 3x minus 6 greater or equal to 0. If I add the 6 over, that's 3x greater or equal to 6, divide by 3. X greater or equal to 2 is the domain. Determine the x-intercept. The x-intercept is going to be where your function is equal to 0. So if you get rid of the inequality and put an equal sign there, that's going to be where x is equal to 2 or 2 comma 0. So there's a link between the domain and the x-intercept of any of these radical functions. Complete this table. Okay. All right, so I'm going to get rid of my g of x function. And this equation, here we go, was negative 3x minus 6. And we want to plug in 2, which gives us 0. Then 3, 4, 5, 8, and 10. So at 2 we have 0. At 3 we have negative 1.732. At 4 we have negative 2.449. At 5 we have negative 3. At 8 we have negative 4.243. And at 10, negative 4.899. Sketch graph. Let me shrink that up. Okay, because of the negative coefficient, this thing's heading downward, and we knew it started at 2 and went for values larger than 2, right? X is greater or equal to 2, and getting larger, negative. So that is our picture. Determine the range. Okay, so again, we can see the picture right here. The range for this, the domain was x had to be larger than 2, but the range, the highest that this function gets is a y value of 0. So the range would be that y is less than or equal to 0, or if you wanted to write this in the interval notation, it would be negative infinity up to 0, because 0 is the highest y value achieved. Does the graph have a maximum value? Yes. The maximum value is going to be at this top point right here. It's going to be at the ordered pair 2 comma 0. The maximum value is usually attributed to the y value, so the maximum value is 0. And it's at the ordered pair 2 comma 0. Okay, that's the highest height that the function achieves is 0. All right, new function. Consider the function x squared plus 4. So we want the domain first, square root of x squared plus 4. And so the domain we find by setting the inside greater or equal to 0. So x squared plus 4 greater or equal to 0. If I subtract 4 from both sides, x squared greater or equal to negative 4. Now I'm going to stop for a second because x squared is positive, right? No matter what I plug into x squared, it's positive, and it has to be greater or equal to a negative 4, and that's going to be always. So the domain for g is all real numbers. Because there's never ever going to be a number that I plug into this that's going to cause x squared plus 4 to be less than 0 or equal to 0 for that matter. All right, so I'm going to call it f because I already have my function named f here. Don't want to change my table. We're going to do x squared plus 4, and our inputs need to be negative 4, negative 2, 0, 2, 4, and 6. Okay, so for -4, I get 4.47. For -2, 3.61. For 0, 2. For 2, 2.83. For 4, 4.47. And for 6, 6.32. All right, so let me uh, move over and see what this function looks like here. Much different shape than we saw before, and that's because the inside had a square in it, whereas the other ones did not. So we'll draw this. Notice that it's not a parabola. A parabola would not be that wide. It's kind of coming in almost straight looking until it reaches its bottom, and then it's heading out straight looking. It's not really curved. These look straight, right? Straight lines coming out. So it's much less curved than we would imagine for a parabola. All right. Determine the range. Okay. The lowest value achieved for this thing right here is at 2. So I'm going to turn off my dots just to make sure. I'm clicking on the correct spot. The lowest value achieved is 2. So the range is going to be y needs to be greater or equal to 2, or I like to write these in interval notation as 2 comma infinity. Okay, so y greater equals 2 or 2 to infinity. Does the graph have a maximum or minimum value? It's got a minimum. So the minimum at, it's 0 comma 2, minimum at 0 comma 2. So the minimum value is 2. 2 is the y value, the lowest y value, and I achieve it at the ordered pair 0 comma 2. All right, another function. This one is the square root of x squared plus 4, where the 4 is not inside the radical. They want us to fill in the same chart here. So I'm going to have 8. Oops, that's a -3. It wants to be at, oh, I did that wrong in the last one. I'll have to go back and fix that. Okay, so that's a 6. You can just fix your own number. I got my number mixed up. Okay, then I got a 4 and a 6 and an 8 and a 10. Okay. So, what they would really like us to know about this is that it is not the same in these two tables. They are not the same. So the square root of x squared plus the square root of 4 is not the same as the square root of x squared plus 4, the quantity. So they are not the same. They're not supposed to be the same either. Okay, graph them. The pictures are different as well. This one comes down to a point. If I graph both of them together, I can see very much not the same graph. Okay, so how do the graphs compare? Well, they're not the same either. So no, the two expressions are not the same. So they're trying to reinforce this idea that you cannot separate a square root over a sum. It is not the same function. You cannot take the square root of the two pieces separately. So that's an important fact about radicals, that you cannot take the square root separately. They are not equal. We can take the square root of a product separately, but not the square root of a sum separately. All right. And then one more thing about the radicals, just to carry back into chapter 2, is our square roots can be written as 1/2 power. So we're going to graph this function with both notations and just make sure that we're getting the same picture. So let me get rid of my table. And once I'm going to use the square root of 3x minus 2, and the other, I'm going to use 3x minus 2 to the 1/2 power. And I should be able to tell the two functions are equal. It might be easier if I dotted one of them. And I can see they are the same thing. So my line is beautiful curve. It's not a line. I shouldn't use that word. But they're the same. So that's what my curve looks like. And we got a quick question about its domain. And so again, for the domain, we need 3x minus 2 to be greater or equal to 0. Add 2 to both sides. That's 3x is greater or equal to 2. Divide both sides by 3. That's x greater or equal to 2/3. So that would be the domain. Or we could express this as 2/3 comma infinity. Okay. Number 13, looking at space and radicals. So according to Einstein's theory of relativity, time would pass more quickly on Earth than it would for someone traveling in a spacecraft close to the speed of light. As a result, a person on Earth would age more rapidly than a space traveler. So the formula A equals the F times the square root of 1 minus V squared over C squared models the relationship between the aging rate A of the astronaut, the aging rate F of the person on Earth, V the velocity, and C the constant. C is the speed of light, about 186,000 miles per second. Okay, so I got to write this equation up over here. A equals F times the square root of 1 minus V squared over C squared. And C is 186,000. That's a constant for C. All right. So let's suppose that you're in a spaceship traveling at 80% of the speed of light. So I'm not actually going to need to put a number in yet for C. I might have to do that later. I don't know. I'm going to put in 0.86 times C for V. So what is your aging rate compared to that of a person on Earth? Okay. So my aging rate is going to be F times the square root of 1 minus 0.8 C squared over C squared. That's F times the square root of 1 minus, this square we know is going to affect the 0.8 and the C, so we need to figure out what 0.8 squared is. Take 0.8 and square it, and you get 0.64. So I'm going to have 0.64 C squared here over C squared. So the reason I didn't put the number in for C squared is because it would have just put a bunch of huge numbers in here for no reason, because the two C squareds cancel. Okay, so this is going to give me F times the square root of 1 minus 0.64 and 1 minus 0.64 gives me 0.36. And the square root of 0.36 is 0.6. So this is going to be 0.6 times F. So what is your aging rate compared with that of a person on Earth? The astronaut's aging rate is 60%. So the aging rate is 60% of the rate on Earth. Right? So that 0.6F means it's 60% of the rate on Earth. If they're traveling at 80% of the speed of light, they're going to age at a rate of 60% of the rate on Earth. So if I'm traveling at 80% of the speed of light for 1 year as you perceive it, approximately how much time has passed for a person on Earth? In this case, the 1 year is the astronaut's perceived rate. So this is our A. So in our equation, as we've modified it for this 80% here, we have A equals 0.6F. So if 1 year has gone by for the astronaut, how much time went by on Earth? I'm going to plug in 1 for the astronaut and divide both sides by 0.6 to get F by itself. Okay, so if we divide by 0.6, 1 divided by 0.6 is 1.66. So 1.667 equals F. So if you're traveling for 1 year at 80% of the speed of light, 1.67 or 1.667 years went by on Earth. Okay, now we're going to suppose something a little different. Suppose that we're traveling at a velocity very close to the speed of light. We're going to put c in for our velocity and interpret our results. So it's practically at the speed of light. So we're going to let our velocity be c. So here we'd have a equals f times the square root of 1 minus c squared over c squared. And c squared over c squared is 1, so that's square root of 1 minus 1. And that's the f times the square root of 0, which is 0, so f times 0 is 0. And so the interpretation of this would be that if you're traveling at the speed of light, your age is never going to increase. It's a theory. In a lot of sci-fi shows, they use this theory. So we travel at the speed of light. You don't age. Right. Okay, so that finishes that example. Again, just a context in which a radical is in an equation. We're going to look at another context in which a radical is in an equation. This is the escape velocity, minimum speed that an object must attain to escape a planet's pull of gravity. In this equation, the escape velocity is capital V. G is the gravitational constant for that planet, and m is the mass, and r is the radius of the planet. So we're going to use Earth. Earth's mass is 5.97 times 10 to the 24th. Its radius is 6.37 times 10 to the 6th. We want to determine the escape velocity, round to the nearest whole number, and we're going to use the gravitational constant of 0.667 times 10 to the negative 11th. Okay, so our escape velocity is going to be computed with the square root of 2 times g, that's 6.67 times 10 to the negative 11th, times m, which is the mass, that's 5.97 times 10 to the 24th, over the square, inside all of this still, the radius, which is 6.37 times 10 to the 6th. Now, all of that's just a number, so I can just type that right into Desmos to evaluate this number. Okay. So I want to do the square root of the fraction 2 times 6.667 times 10 to the negative 11 times, make this bigger, 5.97 times 10 to the 24th over 6.37 times 10 to the 6th. Okay, so my escape velocity is going to need to be 11,178.86. Look at my units here. So kilograms cancel, meters cancel, and I'll have meters squared and seconds squared. So the square root of squared gives me meters per second. Square root of meters squared, square root of seconds squared gives me meters per second. So if you can manage to travel at 11,176.86 meters per second, you can escape the pull of gravity.